So root locus, right? We're talking about root locus. So root.
So can I ask one question real quick?
Please.
So the two diagrams here is B supposed to be like what A reduces down to, or are they two different?
No, this is exactly what A reduces to.
I'm sorry, what?
A reduces to B.
Okay, thank you.
Yeah. So first of all, what is root locus? Root locus is the path of closed loop poles as the gain is. So let's focus on this definition. Path of the closed loop poles. Okay, I don't want to take that even. So here, closed loop poles as a function of gain. That's your root locus, okay? So suppose you have, let's say this is 1 for now to make it easy, okay? Suppose this is 1 and G is, let's say your G is, I don't know, your G is, let's say K over, your G is, let's say 1 over S plus 10. Remember this G is open loop transfer function, right? What is this G called? G is open loop transfer function. So I want to make today's lecture the most interactive, okay? Please stop me anytime you want. I'll go very slowly, but I'll make it very interactive. So then this guy is called closed loop transfer function. Okay. So if my GS is 1 plus S plus 1, what will be your, let me call this T, okay? This is T. What is your T? Guys, can you help me? K times G is 10, right? Divided by 1 plus K times K divided by S plus 10. And H is 1, right? We chose H to be 1. Guys, question here so far?
No.
Okay, so let's do this. So now K times, if I least common multiple, right? If I do the least common multiple, what do I get here? This guy goes here. S plus 10 divided by this whole thing, right? S plus 10. And these two cancel each other. Then what are left with finally? Finally, T equals K divided by S plus 10 plus K. Okay, so GS equals 1 over S plus 10 is my open loop transfer function. And TS equals K over, can I rewrite this guy S square plus 10S plus K. This is called closed loop transfer function. assuming h equals 1, right? This is a special case of to make our life easy, because you want to start with a simple problem, right? That's why you want to start with a simple problem. This h equals 1. So now what is the root locus? How does the closed loop pole vary with gain? Okay, that gives you the root locus. So what is how do you find the closed loop pole? Help me. This is the closed loop pole, right? How do you find closed loop pole? S squared plus 10s plus k equals 0 gives you closed loop poles. So let me start with k equals 0. When k equals 0, what do you get? What are the poles you get? Help me. K equals 0, right? So you have s squared plus 10s plus 0 equals 0, which is simply this equals 0. So s plus 10 equals 0. So s equals 0 and s equals negative 10. When k equals 0, you have two poles, pole 1 and pole 2. What are they? 0 and 10, negative 10. Now let's plug in s equals 5. Let's plug in s equals 5. So k equals 5. Wow. Please correct me, okay? If k equals 5, so how do you get the value of, how do you get the poles? This is more like minus b means minus 10 plus minus b squared 100 minus 4ac, 4 times 5, age 1 divided by 2 times age 1. Does it make sense? Negative 10 plus minus 100 is minus 80, right? 80 is 4 times 10. So no, 8 times. Okay, let's do this. 2 times 4 times, oops. 80 is 2 times 2 times 2 times 2 times 2 times, help me, 8 times 5, right? 10, right? That's what my 80 is. So you have these two gives me 1. So this 4 is square root of 5. So this can be written as negative 10 plus minus 4 square root of 5 divided by 2.
Quick question, Professor. Where did the 5 come from?
No, I'm just choosing k because your goal is to vary k and find the closed loop poles.
Okay, I thought that might have been the case. Just making sure. Thank you.
No, yeah, just choose a random value because I chose the multiple of 5 now to make my life easy.
So basically what we're doing is we're just trying out different k values, and then we're getting the two values of the two poles because there's a plus or a minus in the quadratic equation, and then we're gonna like plot them.
Yes.
Okay.
Yeah, that's the root locus, right? Locus is like, you know what locus is, right? Okay. So what is a circle? Circle is locus of a point at some constant distance. Let's say this is 2 meters. Okay. So what is the locus of this point at constant distance from the center? That's called circle, right? Locus. This is P, right? This is O. Locus of P such that P is always at 2 meters from O. Okay, that's the definition of circle. Circle is defined as locus of P such that P is always at 2 meters from O. So if you allow the point P to move around the fixed point O about, at a distance of 2 meters, you get a locus. That locus is called circle. Okay, so that's the meaning of locus. I'm just giving you an example. Similarly, we are going to do this, some kind of locus. Okay, so 1k equals 5. What is the value of pole 1 and pole 2? Pole 1, you get 9.47, and pole 2 you get negative 0.53. Similarly, I choose value of 5k equals 10. You know how to do it, right? So let me give you the exact answer now. Okay, all the answers here. So here, if I do that, I'll get this here. For k equals 0, 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. I did the plot up to 50. And corresponding value of pole 1 and pole 2, 10, 9, negative, all negative. Then at some point, then similarly pole 2, 0, negative 0.5. Then at some point they're exactly equal. Then after that, so up to here it is real, right? See, the poles are real. This is real. Then after that, the pole become complex here. When they become complex, this is, see what this, there is only one difference. Even though they are complex, they are different. They differ by simply a sign here. So the pole are in general, they are different. See, negative 10, 0, like that, right? But here the poles are, they are not same, but they're conjugate, right? I would say, okay, this is plus, this is minus, see? But everything else is same. Negative 5, 2.24. Negative 5, 2.24. Okay, so this guy is plus, this guy minus. That's called conjugate. Okay, this is plus, this is minus. Otherwise, they are same. Now let's plot it. All right, let's plot this pole. Let's plot pole number 1. So let's plot this guy, then we'll do pole number 2. Plot this guy. So when you plot it, what do you get? So k equals 0. For k equals 0, see that k equals 0. What is the value of pole 1? Negative 10. And k equals 5. Now k equals 0 is done, k equals 5. K equals 5. What is the value of pole? Negative 9.47. This is 9. Negative 9.4 would be here, right? Then 10. K equals 10. What is the value of pole? This is 8.87. So this is almost 9, right? 8.87 almost 9. That's why we have it right there. Almost 9. All right. So then 15. 8.1, 15.1, 8.16. 15, 8.16, right here. Similarly 20. For 20, what is the pole? Negative 7.4, somewhere here. Okay. Then 25 is negative 5, right here. This is 25. Then 30. When you have 30, what is the pole? So this is, it has, until now it has just real, meaning x-axis, right? Real means only on the x-axis. Now after that, after this point, it started becoming complex now. Not only you have x, but also you have y. But the thing is, your x is always same. Look at that. X is negative 5 all the time. Then how about the y? Y only changes 2.24. Your x does not change. X stays the same here. Only the y. For 30, 2.24, somewhere here. See, this is 2. This is my 30. Now for 35, 3 plus 1, 4. 35 is 3 plus 1, 4. This is 3, slightly more than 3, somewhere here. Then 40, this is 40. which is 3.87, so close to 4, somewhere here, close to 4. That's it. And then 45, you have 4.47, somewhere here. Then 50, you have 5. Then, now look, this guy started at -10, and it goes like this. Do you see that? It started -10 and goes like this. Similarly, this is for pole 1, right? Similarly, if you do the pole 2, what do you get? So you start with 0, right? See, you start with 0 here. This is your 0. Then you have negative, this guy here. This is for 10, this is for 15, this is for 20. It comes this way, okay? Then at 5 is -5, 25 is -5. Then now this one is plus, everything was plus here, right? Look, that's why the branch was up. Now this is minus here, or everything is minus. That's why the branch goes down. That's why branch goes down like this. Does it make sense?
Yeah, that makes sense now.
Okay, this is pole 1, and this is pole 2. So how many branches of, this is called root locus, okay? So both the, now you have, this complete picture is called root locus. So there are many advantages to the root locus. One of the advantages is that for what value of k, my system is stable. For what value of k, let me ask you the question. For what value of k, system is stable? That will be answered by this root locus. How? So if the pole is, root locus is what? Root locus is the path of the pole, right? With the varying, with different value of k. Okay, k versus pole. That's the root locus, right? If the pole is on the left half plane, right? Left half plane. Then what is that system called?
Stable?
Stable, right? Meaning for this system, right? For this system, what system? This system. For this system, rather this system, right? This is the closed loop. For this system, you can take any value of k. Any value of k makes your system stable. That's the good news, right? You don't have to worry about what value of k you want to choose. Choose any value of k, your system is stable. But the thing is, you know, depending on what kind of system you need, you have to have the proper value of k. That's you know, that's what you need to do. But the thing is, no matter what the value of k you take, your system is stable, because this guy never goes to the right half. See that? The root locus never crosses this axis and go to the right half. Meaning for any value of k, your system is stable. That's the one of the advantages of root locus.
Even if we took a, like, let's say -1?
-1, which one?
Like if we took like a negative, k equals -1 or k equals -5.
Oh, we don't do that. So for
We
now, let's
don't
make
do
our
that?
life easy and make this
Oh.
greater than 0.
Okay, cool.
Yeah, that's a good question though. Yeah, that's a very good question. So for now, to make our life easy, because this is introductory course, so we don't want to go to, you know, every details. So we try to make our life easy as much as possible. So now the thing is, this is tedious, right? So you don't want to, you know, do the calculation every time to figure out the root locus. Okay, this is a tedious process, looks like. But is there an easy way out to find the root locus? There are some rules to draw the root locus. Okay, so that's what we are going to cover now. Rules for drawing or sketching the root locus. Okay. All right, so let me come back here. The rules, now the good news is that, okay, remember I did here two transfer function, right? One the open loop, the other one is closed loop. You might have, okay, so it's here. I don't have to say anything else. All right, so you see there are two transfer function, right? One the open loop and the closed loop. So which one is easier to deal with? Can you help me here? You have to help me here, please. Which one is easier to deal with? Open loop or closed loop?
Open.
Open loop. Okay. It is easy to deal with open loop, but what do you need? You need the closed loop poles as a function of gain. Your goal is to vary gain and find the closed loop poles, not the open loop poles. Okay, this is not open. Okay, this is closed. Vary gain and find closed loop poles, not the open loop. But open loop would have been easier. You already said, right? Open loop would have been easier. Now, there are some rules that we can do the, root locus, which is gain versus closed loop poles. We can plot this picture. But that rule depends on open loop poles. That's the good news. Okay? There are the rules that we are talking about. Rules for what? Rules for sketching root locus. Root locus meaning closed loop poles, right? Closed loop poles versus gain. That's the root locus. Fortunately, those rules depend on open loop poles. Good news, open loop poles. Those rules rely on open loop poles. In some way, open loop poles give me the idea about closed loop poles. Isn't that exciting? That's what I'm going to do now. I'm going to find the rules for sketching root locus, meaning closed loop poles versus gain. But those rules depend on open loop poles. That's the big good news. That's what I'm going to do now, okay? Let's start with rule number one. Rule number one, again, for now, we strict ourselves, we confine ourselves within this region, okay? K greater than 0. So how many branches of root locus you will have? So how many branches do you see here? 2 branches, right? One for pole 1, one for pole 2. You have one branch going from here to here, the other branch coming from here to here. Okay? What rule number 1 says is number of branches of the root locus, number of branches of the root locus is equal to number of open loop poles. Look at that. You just find the number of open loop poles from here, not from here, not from here. Find the number of poles from here. So if you have 2 poles from here, it means you'll have 2 branches. Isn't that a good news? You don't have to talk about this guy. Even though you are working for this guy, you are working for this guy, you are working for closed loop transfer function. Even though you are working for closed loop transfer function, you just rely on the open loop. So number of open loop poles is equal to number of branches of the root locus. Guys, make sense?
Yeah.
Okay, let's do rule number 2. Rule number 2, the root locus is symmetrical about real axis. What do I mean by that? So you have two branches of the root locus here, right? This is branch number 1. This is branch number 2. But they are the branch of a root locus, right? This is a combined system now. This is a combined system. Even though you have 2 branches, those 2 branches are the branches of one system. That is root locus, right? They are the root locus, branch of root locus. So is this entire system symmetrical about real axis? What is symmetrical about real axis? Is this guy symmetrical about real axis? Oops. Okay, so if this guy, this is symmetrical about real axis, and this is symmetrical about imaginary axis. See that? That's the meaning. So meaning if you fold in half along this line, then they are identical. That is symmetrical about y-axis. If you fold in half along this line, such that they are identical, the 2 halves are identical, then you call symmetrical about x-axis. In this case, if you fold this guy from here, this axis, real axis, do you think your branches are symmetrical about x-axis? Just they exactly overlap to each other, right? So that's what I meant. It always happens. Root locus is always symmetrical about real axis. Guys, make sense so far?
I mean, I guess it does. But like, I mean, it doesn't. I don't know. It doesn't seem exactly symmetrical to me though, because like pole 1, for example, when it's on the real axis, is all below -5, but pole 2 on the real axis is all above -5. But I guess because it's like laying right on the axis, it's like, I guess, counts as symmetrical.
No. Okay. No, that's okay. That's okay. So let me tell you. So what do you mean as symmetrical over x-axis? Is this guy symmetrical over x-axis?
Yeah, I mean, I got your examples, but I'm trying to apply it to like the plot that you made of the pole 1 and the pole 2.
Yeah. So let's fold it from the real axis. Let's fold this guy. So we have a paper, right? Let's say fold it from the. Suppose you have a paper exactly. You have the lines drawing like this, right? When you fold in half, this guy exactly overlap with this guy. Do you believe that?
Yeah, I guess it's the other part that they're not the same.
Which are not?
But so like the part of that each plot where it's on the real and not on the imaginary, like, so pole 1, right, is only exists on the real axis below -5, and pole 2 only exists on the real axis and values greater than -5. So I don't know. I guess because it's laying right on the real axis, like it's not a little above or a little below, I guess it's still symmetric. I don't know what I'm saying.
Try to understand.
Yeah.
Okay, so are you talking about this portion?
Yeah.
This
Because
portion?
they're different, right?
No, this is. Oh, I see. So you are talking about this guy and this guy.
Right. But I guess
Okay.
but because it is right on it, maybe that's why it's still symmetrical.
Oh, I see your point. So,
Okay.
I see your point. So this guy, so is this point symmetrical over x-axis?
I mean, I guess it is because it's laying right on
Yeah, when you
that
pull it back,
x-axis. Yeah,
it is point, right?
yeah,
So that's why it is symmetrical also, because
it's just a point right directly on the axis.
exactly.
Okay,
That's
that's
why.
all I just wanted to make sure I
Yeah,
was understanding.
yeah. When you fold it, this axis is symmetrical with this point is symmetrical with itself.
Yeah,
This point is symmetrical with itself. This point is symmetrical with itself.
yeah.
This is how it
Okay.
works.
Thank you. I'm sorry that was
No,
hard to
that's okay. So
explain.
does it make sense now? It makes sense now, right?
Yes, it does. Thank you.
Okay, all right. You have to take every point, okay? That's what it is. All right, good. I'm happy. Okay, now let's move on to the, so you understand rule number 2. Yeah, that's the kind of interaction I want, guys. So please do ask me a lot of questions. So now number 3, rule number 3, the real axis segment. Now we know the locus is a line, right? Locus is a line. Okay. Now this line might cross the x-axis some point, right? This is a line. Suppose you have a line. Okay, so let me make it different here. So your line is this now. Your line, your locus, I don't know, your locus is symmetrical like this, let's say. Okay, so this locus passes through this point. I'm just talking about this point now, okay? Just real axis point. All right, so what are the open loop poles? Again, we talk about open loop poles. What are the open loop poles in our case? Do you remember? From here. What are the open loop poles from here? S equals 0 and S equals -10. So this is, let's say, S equals 0. Okay, this is, let's say, S equals 10, -10. This is 0. Okay. Now this rule says valid region of the root locus are to the left of odd number open loop poles or zeros. So how many poles do you have here? 2, right? You don't have more than 2. You just have, this is pole 1, this is pole 2. Now you have to number this guy. Once you put, oh, this 0 is right here, right? Sorry, this 0 is right here. This is my 0. This is my -10. Okay. So now you start, suppose you are here, you start counting from the right. You always start counting from, this is the rule, okay? Count from the right side, not from the left side. Count from right. You have to always do that according to this rule. You start counting from right to left. All right, so which one is number 1? If you count from right, this is number 1, this is number 2. Do you have more than 2? No, right? Now which one is odd? Which one is even? This is even, right? This is odd. This is odd. This is even. 2 is even, 1 is odd. Okay? Now your root locus passes through the left of odd. So this is your odd, this is the left of odd. And suppose you don't know root locus at, okay? You don't know root locus, but you're just trying to, because you want to use some rules, right? You don't know the region. You don't know where the root locus passes from. How does it look like? So then your root locus, now does your root locus passes through this, or does your root locus passes through this? That's what I'm asking. Can you help me here?
So you're saying it passes somewhere in between the S equals 0 and the S equals -10?
Yes.
Okay.
This is n equals 2, right? So it always passes through left of odd number. But how about this guy? This is not left of odd number. This is the left of the even number. See that? This is the left of even number. That's why root locus does not passes through this guy. the root locus passes through this guy, this section. That's what rule number 3 says. Root locus are to the left of odd number open loop poles and 0. So it could be 0 also. Suppose you have 1 0 here. Let's say you have one more 0 here, s plus 1 on the top. Okay, then how do you do that? In this case, what will you do? What are the poles? Poles is 0 and negative 10. And what is the 0? Negative 1. This is n equals 1. This is n equals 2. This is n equals 3. Now, can you guys tell me where the root locus will pass through? Which region? Guys, you guys need to help me here, okay? I'm lost.
Would it pass through to the left of n equals 3 because you have added in the n equals 2?
Yeah, either here or here.
Okay.
So we don't know where, but we at least we can't find our region, right? Even though you don't know where does it exactly go through, but we know the root locus doesn't go through here. We can't find the region. So it's always left to the odd number. This is odd, this is odd. Left to the odd, left to the odd. Not left to the even. Right, makes sense? Any questions?
Yeah.
Okay. Now let's do the rule number 4. All right, rule number 4. Rule number 4 is starting and ending point of the root locus. So it always start with k equals 0. Remember we did k equals 0? So here, k equals 0 belongs here, right? And here. These are the starting point. Always begins with k equals 0 and always end at k equals infinity. But remember, it always start with 0, always end at the k equals infinity, or let me rephrase it. I don't want to say, okay. This is what I'm going to say. So start means k equals 0, right? That's what you understand. So the k equals 0, it starts at negative 10. The part 1, branch 1, right? Branch 1 start here. And branch 2 start here. This is branch 1, this is branch 2. They always start at the pole, not 0. Remember, you have pole and 0, right? Pole and 0. They always start with pole and they always end at 0. That's what I'm trying to say. They always start at pole and end at 0. But you might ask me a question here. You know what? You will ask me a question. I know that. But this guy, what is this guy? Our s equals s 1 over s plus 10, right? So how many poles do I have here? I have 2 poles. S equals 0 and s equals negative 10. But according to this rule, what did I say here? I always start at pole and I always end at 0. But how many 0 do you have here? No zeros. That's the problem. You have 2 poles, but you don't have any 0. See, you don't have anything on the top. The top will give you 0, right? You don't have anything on the top. Then what do? The rule says it starts at pole and at 0. But you don't have 0 there. What do? In that case, what happens is they always go to infinity and we call it zeros at infinity. If you don't have zeros, then they end up going to infinity, and we call them quote unquote zeros at infinity. Guys, does it make sense? Question here, please.
I think I get that.
Okay. All right, let's do the number 5. All right. Now let's talk about the behavior at infinity. How does it behave at infinity? How does the root locus behave at infinity? So we say if you don't have 0, right, then your root locus go to infinity. You understand? So if so, then how does it go to infinity then? So this guy is going straight, right, 90 degree. Why is this guy going 90 degree as shown? Why is this guy going, negative 90 as shown? How do I know it goes 90 degree or 60 degree or 30 degree? It goes to infinity, but does it go this way? Does it go straight up? Or does it go like this? In the same way, does it go like this on the other side? How do I know which way it goes? That's what I'm trying to figure out. That's what I call behavior at infinity. Okay, so root locus approaches straight line as asymptote as the root locus infinity. Further to find the behavior of those asymptote, we call it asymptote, right? Asymptotes. To find the behavior of the, or to draw the asymptote, we have to find the angle and the intercept. So where exactly where on the x-axis those asymptotes meet. So how about this guy? In this case, these are my asymptote, right? And my root locus goes like this along the asymptote. Okay, my root locus starts from here and goes along the asymptote like this. Similarly, on the other side, it goes like this. But the thing is, where do those root locus meet on the x-axis, on the real axis? That point is called real axis intercept. In my case, what is sigma a? -5. Look at that. My sigma a is -5 in my case. That's called real axis intercept, or some book says centroid. Not only the point. Now you got the point, right? You got the point. But how does it go? 90, 30, 60? So that angle is given by this formula. And that intercept is given by this formula. Let's apply these two formula in our case. How about that? Okay, so what does the formula tell us? Our formula says, so number of finite poles. Add all the finite poles. Add all the infinite zeros. Remember, this 0 is called 0 at infinity, right? Okay, that's not what we are supposed to add. Only finite one, okay, not the infinite ones. That's what it means. Add all the finite poles. Add all the finite zeros. Then subtract them. Then divide by number of finite poles and number of finite zeros. That gives you sigma a. Let's do that. So sigma a equals, how many finite poles are here in our case? 1 over, again, s plus 10, right? So how many finite poles do we have? S equals 0 and s equals 10. 2, right? So you have to add both of them. So -10, sorry, this is -10. -10 and 0. This is what this guy is. Sum of all the finite poles is this. Now how about, and this have minus sign here. This is minus sign here. Now how about this guy, finite zeros? How many finite zeros we have? None, right? Then add them all together. That's what you get, 0. You don't have any. Top part is done, right? Top is done. Now let's do the bottom part. How many numbers of finite poles? How many numbers of finite pole here? 2. That's what it is. How many numbers of finite zeros? None. Then what happens if we add all them together? Negative 10 plus 0, negative 10 minus 0, negative 10. 2 minus 0, 2, which is negative 5. Ta-da! That's what we know, right? It works. How about the angle? Our angle should be 90, right? Because they are going like straight up. Let's use this formula and see whether our angle is 90 or not. So here the formula is 2 times k plus 1 times pi. Then number of finite pole and number of finite zero. They are exactly the same as before. These are exactly same. These guys on the bottom are exactly same. Only the top is different. You know, you have this guy on the top, you have 2k plus pi on the top. That's the only difference here. So 2k plus 1 pi. Let's do that. So before you do that, you have to figure out what is the value of k. How do you figure out the value of k? Your value of k is given by this formula. What is the, always k start with 0, by the way. K always start with 0 and here. So this is the value of k. K always start with 0, 1, 2, dot, and here. This is the end point of k. In this case, what is the end point? Help me. Finite pole. What is the number of finite pole? 2, right? Minus, what is the number of finite zeros? 0. Then you have minus 1 as in the formula. Then this minus 1. Then what do you get? 2 minus 0 minus 1, 1. So this k and at 1. Not, you don't have to even go to 2. So you have 2 k's here. You don't have more than 2k, which is 0 and 1. So that's how you figure out your k. Okay, by the way, this k is 0 and 1, meaning there are 2 asymptotes. That's how you say. 2 asymptotes there. Because you have 2 values of k. If you have 2 values of k, means you have 2 asymptotes. So let's see whether we have 2 asymptotes or not. Okay. So your k is 0 and 1. So let's put k equals 0 here and k equals 1 here. Look at that. So what is the finite number of pole minus finite number of 0? What is this guy? I mean, finite number of poles is 2, right? Finite number of 0 is 0. That's why on the bottom we have 2. 2 minus 0 is 2. On the bottom we have 2. On the top, let's do the top. You have 2k plus 1 plus pi, so times pi. Times pi is there. And 2k equals 1 plus 1. So k equals 0. Sorry, 2 times 0 plus 1. That's for k equals 0. Similarly, k equals 1. Okay, you got these two here. These two. Theta A and theta, theta A. There are 2 thetas there. So what does this give me? Let's simplify this. Is this pi over 2, which is 90 degree? How about this guy? 3 pi over 2, which is 270 degree. Let's do that. So you are going from here. This is pi over 2, 90 degree. And this is 180. And this is 270. See that? We have 2 asymptotes, one going up, which is 90 degree. The other going down, which is 270 degree. Guys, question here, please. Question, please. I have one more rule. There are other several rules, but I'm not going to go through them. So if you have one more rule, then it will do it. Okay. Let me do one more rule, then I'll have one more example, then I'm done. All right. So next rule, number 6. Rule number 6. We're talking about breakaway point and break-in point. So we know the root locus start from the pole, right? They start at pole, and they end at start at pole and end at 0, right? Okay. Suppose you have 2 zeros here. Let's look at this picture here. How many zeros you have? You have this 0 and this 0. Sorry, pole, right? These are poles and these are zeros. So you have 2 zeros and 2 poles. Okay. All right. So how does this guy go from here to here? Okay, this will go this will go here, right? This will go here. How does it go? It will go this way and go this way. How does this guy go? Other guy. How does the other guy go? It starts from this pole and this guy go this way. And go this way here. So this pole goes to that 0 and this pole goes to this 0. Okay. Now there are points called breakaway point and break-in points. So here, look, this guy is going here this way. This guy is going down here this way. But here, this guy is coming down this way. This guy is coming this way. Which is breakaway point, which is break-in point? Now, can you guys decide? One is breakaway, the other one is, okay. Which one is which? Left. Is the left breakaway or break-in? Is the right breakaway or break-in? Guys, you guys have to help me here. What do you think? This guy is breakaway. This guy is break-in. Okay, so let's conclude it. So if you have 2 poles, right, then the root locus break away from some point in between poles. Between these 2 poles, they break away from here. This goes this way, the other guy goes this way. They break away. And here, they break in. Those points are called break-in and breakaway points. By the way, when you break away and break in, what is the angle here? Why don't they break like this? Break away like this? Why did they directly go up like this? This angle. Why is it exactly looks at 90 here? Why the angle is 90? Because the rule is this, 180 over n. You have two branches, right? That's why n equals 2. So 180 over 2 is 90. That's why they break away or break in at 90. Question here.
Can you maybe explain the picture again?
No, I'm not going to explain the picture, but I'm just trying to make sure you understand breakaway and break in.
I guess I don't totally get it.
Okay, all right. So let me explain it then. So we'll not worry about the entire picture. We just worry about the breakaway and break in. Okay, so this is my pole, right? This is my 0. So what is the rule? What did the previous rule tell us? Rule number 4. Starting point is pole, right? Starting point is pole, ending point is 0. We have 2 poles and 2 zeros, right? That's good news. For each of them, there is a pole. Otherwise, it has to go to infinity, right? If you don't find enough zeros, if it doesn't find enough zero, let me rephrase it. I think I said something different. So for each pole, you have to have zero. So the root locus start at pole and end at zero. So we have 2 poles, 2 zeros. That's the good news. It means our root locus does not have to go to infinity to find zero. Okay, so it starts at this pole and end at this pole, this zero. It starts at this pole and end at this zero. While doing so, okay, while doing so, this guy has to go through, this guy has to have some path, right? This guy goes through here and goes this route. Suppose I'm just talking about these two only, okay? Why the path is like this? I don't have the function at, right? So that's why I cannot explain that path. Why is it circular? I'm not going to explain that, but I'm just trying to explain this part only, okay? These two part only. So here, this guy starts at the pole, and from here it goes like this and comes to the zero. Similarly, the other guy, other pole goes from here and goes here. So what is this point? This goes, look, this guy goes from here and here it break away. One is going up, the other one is going down. Means they are breaking away, right? How about here? It goes here and comes here. And similar, this guy goes here and comes here. What is this point? Break in. See, they are coming together towards this point. They are coming in. That's why this point is called break in point, and this point is called breakaway point. Just I am trying to make sure you understand the concept of breakaway and break in points.
Thank you. I think I understand it better now.
Okay, all right. Very good. Now, next thing I explained it here is what is the angle of the break in and breakaway points? What do the angle? Do they break away like this or like this? How do I know? Because I have a formula. So 180 over n. So how many branches do I have here? One branch this way, the other branch this way, right? That's why you have 2 branches. So meaning n is 2, which is 90 degrees. That's why whenever you have 2 branches, then they always break away or break in at 90 degrees. Does it make sense? Guys, any other question? All right, let's do this then. Let's do one problem, then I'm done. All right, we have all those 5 rules. Now 6 rules, let's implement them, okay? All right, so this is my open loop transfer function, right? Now my h is 1 again to make my life easy, h equals 1. Now let's use the number of branches. How many branches are there? What is the number of branches? How do you know number of branches? The number of poles of open loop transfer function. This is the open loop transfer function. What is the number of poles of open loop transfer function? S equals 0, S equals -1, S equals -2, S equals -4, right? These are the, how many? What are the numbers? I don't care about the number for now. 5, -2, 6, 100, I don't care. But how many? 1, 2, 3, 4. That's why I have 4 branches. Number of branches will be 4. Now remember, when you draw the root locus, you have to have 4 branches. Okay, keep that in mind because that's what rule number 1 says. Now, okay, one thing is fixed. We have to have 4 branches. All right, so this guy, 4 branches. Now, symmetry. The root locus is symmetrical about real axis. Once we draw it, we'll see it, okay? Don't worry about this for now. So rule number 2. Now rule number 3. What is the real axis segment for this guy? What is the rule? The left of odd number open loop poles are 0. So how many poles are here? You have to plot them now. So s equals 0 is here, right? This is my s equals 0. What is s equals -1 here? -1 is here. S equals -1 is here. Then s equals -2. S equals -2. Then s equals -4. S equals -4. I have how many poles? I have 4 poles. 0, -1, -2, -4. 0, -1, -2, -4. I have 4 poles. So how about 0? See, you have to set the top numerator to 0, right? To find zeros. So what do you get from here? What is 0? -3. That's what I have here. This is -3. This is the 0. See, 0 is represented by 0 and pole are represented by cross. That's the standard rule. Now, right, let's find the real axis segment, which is left of odd number open loop zeros and poles. So we have all zeros and poles together. Look, everything is together here, zeros and poles. Now, number them from the right hand side. This is n equals 1, this is n equals 2, this is n equals 3, this is n equals 4, this is n equals 5. Okay? Once we number them, then see the left of odd. From here to here is 1 portion. Then from here to here, this is not valid region, okay? And from here to here, this is the another region, and from here to infinity, all the way to infinity. Now, your root locus either passes from here, or passes from here, or passes from here. That's what we know so far. Does it make sense? Rule number 3. Now rule number 4. Now we have 4 and 5 together here. Starting and ending point and behavior at infinity. So now let's use this sigma a. Where do they meet? On the real axis, sigma a. So what is the formula? Finite poles. What is the sum of finite poles? Finite poles are 0, -1, -2, -4. These are finite poles. What are finite zeros? There is only one finite zero, -3. Now add them all together. What do you get? 0, -2, -2, so 0, -1, -2, -4. 0, -1, -2, -4. That's what this guy is. This guy is that. Now what is the number of finite zeros? You have just only one. That's why this minus, then you have -3. Minus, -3. Then what is on the bottom? Number of finite poles. How many are there? 1, 2, 3, 4. That's why we are here. Number of zeros, just only one. Make sense? Then what do you get here? If you add all them together, you get -4/3. Okay? So meaning the asymptote meet at -4/3. -4/3. They go to infinity from this point. Because there should be, how many asymptotes do you think you should have? How many poles do you have? 4. How many zero do you have so far? 1. 4 minus 1 means you need 3 asymptotes. Because always pole start, locus start at pole and end at 0, right? So you have more poles here. You have 4 poles and only 1 0. So how about 3 for other 3 poles? For other 3 poles, you need to find zeros, right? Those zeros are at infinity. That's called 0 at infinity. Okay? So that's why you have 3 asymptotes. You have to have 3 zeros at infinity, meaning you have to have 3 zeros, 3 asymptotes. Okay? Now, let's do the theta A. So what are the 3 angles for those 3 asymptotes? Let's figure that out. Theta A equals, the bottom is same, right, as before here. So which is 3, right? You have 3 here. That's not a problem. How about the top? You know you have 3, right? So k equals 0, 1, and 2. That makes 3. 1, 2, 3. K equals 0, 1, and 2. So let's plug in k equals 0 here. So k equals 0 gives me this. K equals 1 gives me this. K equals 2 gives me this. What are they? This is 60, this is 180, and this is negative 60, which is 300. Remember this, out of 4 finite poles, 1 ends at open loop 0. Out of 4, these 4, out of 1, 2, 3, 4, one of them goes to this minus 3, and rest 3 and at 0 and infinity. It means if a pole does not have a friend, which is 0, it goes off to infinity to find it. All right. Now let's do that. So how about the number 6, rule number 6? If the branch on the real axis lies on the pair of poles, now let's do that. So what is this guy? This is s equals 0, right? This is s equals, help me? S equals negative 1.
Negative.
Go ahead.
Oh, yeah, I was just going to say negative 1.
Yeah, s equals negative 1. This is 0. This is negative 1. This is
Negative 2.
2. This is negative 4. And this is 0, right? This is 0, which is negative 3. Look, now let's use all the rules. So this is negative 4 over 3. Remember, we found this guy here. Negative 4 over 3. Negative 4, this is sigma A. Right here you have to have, 3 asymptotes. So what are the angles for the 3 asymptotes? Let's begin with the asymptotes first. What are the angles for the asymptote? Help me, guys. 60, 180, and negative 60. 60, 180, and negative 60. You have 3 asymptotes, 60, 180, and 60 degree, negative 60. Meaning, so this is negative 4 over 3, right? This is negative 4 over 3. At this point, you have 3 asymptotes. You have 180. This is one asymptote, 180. One is 60, right? Oops, I don't know. Should I make it like this? This is 60. And other one is negative 60. So we have 3 asymptotes. We drew that, right? So we have the poles, we have the zeros, we have the asymptotes. Now, so how about this guy now? So now let's talk about this negative 4. This is negative 3. This is negative 2. This is negative 1. This is 0. So what do you think this negative 2 go to? You should find the 0 right here. Look at that. This negative 2 goes to negative 3. I'm almost done, okay, guys? This negative 2 goes to negative 3. Pole goes to 0. How about negative 4? Negative 4 goes along this asymptote. See, it goes all the way like this. This is what. So negative 2 is done, which goes to negative 3. Negative 4 is done, which goes to infinity. Now, how about negative 1? Negative 1 goes like this. Negative 1 goes from here and break away here. Remember, break away at 90 degree and goes along this asymptote towards infinity. And this one goes along this and break away again to infinity. We kind of know the pattern of the root locus now. Does it make sense? And remember, this is symmetrical about real axis. Okay, see this locus. 1 is this. How many branches we should have? We should have 4, right? 1, 2, 3, 4. This is predicted by rule number 1. We have 4 root locus. 1, 2, 3, 4. Rule number 2, symmetry, right? See, this is symmetry. Rule number 3, real axis segment. See, my left of real axis segment means this guy. This is n equals 1. This is n equals 2. This is n equals 3. This is n equals 4. And this is n equals 5. It happens left to the R. See? Right here, left to the R. See, it's not there. Left to the even, no. Then here, n equals 3, left to the R is here. N equals 4, no. N equals 5, left to the n equals 5, it goes to infinity. Okay, with that, I conclude this. So, but this is just the estimate, right? We did not plot all those data here. We did not plot all those data here. This guy, we didn't have all the data, right? This is just the estimate. So according to this, based on this asymptote, we just guess that these are the points because it goes, it meets asymptote at infinity, right? That's the assumption, right? So that's why we don't know the exact picture, but we know the tentative picture of the root locus here. How do you get the exact plot? You have to go to MATLAB. Or there is online resource. If I click here, if you have a minute, if you click here, this awesome website, I found it last time. Oops. So I found it here. So you can just simply, what is it? It's simply go here. I think drawing tool. Yeah, drawing tool. If you go down here, what is the drawing tool? Let me click drawing tool. Right here, see? You can simply, what is our thing? So S plus 3 on the top. What is on the bottom? S times S plus 1. Help me, guys. Do you have it? S plus 2. Guys, are you there?
S plus 4 is the last one.
Yeah. So if you do that, so then it gives me that, and from there, look at that. Look at that. See? We got exactly what we had before. So if you zoom in, you can see bigger, or you can, if you want to see the asymptotes, it's there. Or you can use MATLAB. Okay, this is such a cool tool here. I loved it. You don't have to worry about K because K is constant. It does not affect the quality, right? It's just the quantity. So you don't have to worry about K. Just plug in here and get the root locus. With that, I